Hi, my name is Will Sawyer, and it's my pleasure to introduce our poster implementation of the Performance Portable Icon model. This is the work of many people in the icon community, and it's my pleasure to represent them today. So ICON is a modeling system for climate and numerical weather prediction simulations utilizing a subdivided icosahedron, which can be subdivided to any desired resolution. It takes many geophysical processes into account. Our work has led to a performance portable version for GPUs, CPUs, and vector machines, and has good scalability across a wide array of platforms in Europe. It has been used for operational numerical weather forecasting since January of 2015 at the German Weather Service. It does consist of computational kernels, or so-called stencils. It's implemented in Fortran 2008 with MPI for communication and a variety of directives, OpenMP, OpenACC, and NEC directives for performance on different platforms. We were constrained by a 2-decade development cycle, so a full rewrite was not possible. But rather we had to compromise and use these variety of parallelization paradigms. This is an example of a basic stencil kernel, which operates over 3 loops, a blocking loop where the horizontal domain is split into blocks, a number of levels, vertical levels through the atmosphere, for example. And then finally, over the block size can vary depending on the target architecture. The array operator consists of simple arithmetic operations on arrays, but can also include indirection through indexing arrays. There were a number of implementation challenges in our work. There is code divergence, which we've limited to a very few number of places where alternate code is run, for example, on CPU or GPU or vector machine. There are index lists. They are operations on some sort of a mask based on the condition of a mask. If the condition is fulfilled, the indices are put into or collected into lists. Some of these collections were just replaced by an if statement in the full computational loop. Where that didn't perform well, we tried OpenACC atomics. Those had, unfortunately, low performance and were replaced by NVIDIA's Cub library. There's also GPU direct communication, where we bypass the CPU hosts for MPI communication, gives us performance gains of about 5 to 10%. The code does perform very well on modern architectures using Intel Haswell, an old CPU processor, as the basis. We see 5 times improvement in almost all components for an AMD CPU, similar to the NVIDIA P100 performance. Volta brings a larger and faster cache, considerable improvement over Pascal. Then to A100, the increased memory bandwidth gives us additional gains. The strong scalability is very good for CPUs, and as long as the GPU has sufficient thread occupancy, it is also good on GPU. Those are results for pit stained in red and purple at CSCS in the right-hand side, and on the left, Joules Booster at Uli Supercomputing Center. Finally, it does perform also very well on the NEC SX vector architecture, which was not intended to be a machine with excellent strong scalability. But in spite of that, we do see good, strong scalability for a low resolution test case, that's on the bottom in a log-log plot, and then in green and red on a medium resolution for green full physics simulation, and red just the dynamical core. If you'd like more details, please visit our poster, and we look forward to seeing you there.